Now we will see the cofactor matrix and adjoint matrix. Now a cofactor matrix is a matrix in which every element Aij is replaced with cofactor Cij. That is, if we are given a general matrix like this, now if every element of this matrix is replaced with the cofactor, then we say the matrix formed by the cofactors is a cofactor matrix. That is, this A11 is replaced with this cofactor, that is C11. Now how it is formed? We see here A11, the position of A11, and we mentally delete the row and the column in which it appears, and we get these elements. Now the determinant of these elements is denoted by C11. That is, this C11 is here. This is the determinant of A22, A22, A23, A32, and A33. Similarly, this A12 is replaced with its cofactor, that is C12. Now the cofactor of A12 here is, we mentally delete the row and the column in which this element appears and form a new subdeterminant of the remaining elements. Now if we delete this row and this column, we are with this element 1, 2, 3, and 4. That is, the cofactor of this C12 is, that is A21, A23, similarly A31, this element, and A33. Now similar is case with this, when we replace A12 with its cofactor, that is C13. Now if we delete the row and the column in which this element appears, the remaining elements form a new subdeterminant, that is these four elements. Now the cofactor of this C13 is, so for the sake of understanding I will show you. Now this column and this row is deleted, and we are with these four elements, that is A21, A22, A31, and A32. Similarly, we replace every element of this matrix with its cofactor. This process goes on up to we find out all the 9 cofactors. Let us I take the random another cofactor. Now if it is the element A23, now we have to replace it with the cofactor, that is C23. Now here the cofactor will be, we will delete the row, this row, and the column in which it appears. Now we form the matrix of the remaining elements. Now the remaining is this, this, and this, and this. Because we delete this row, we delete here this row and this column, the remaining elements will form another cofactor, that is C23 is here, A11, A12, A11, A12, and A31 and A32, A31 and A32. Now I will not show the all 9 cofactors. You can check it out easily here. Similarly, if we have A31, we have to delete the row and the column in which appears and take the determinant of the remaining elements. So accordingly we will get the 9 cofactors here. Now the matrix formed by these cofactors is called the cofactor matrix. Now in parallel I will give an example. If I have a matrix that is A is equal to 1, 2, 3, 1, let us say this is 4, 6, 8, 2, 3, 5. Now the cofactor of this will be this matrix will be, that is C is equal to, now we will replace every element here with its cofactors. Now the cofactor of this first element is, we delete the row and the column in which it appears and take the subdeterminant of the remaining elements, that is 6, 8, 3, 5. So the first cofactor will be 6, 8, 3, 5. So this is the first cofactor. Similarly, for 2 we delete the row and the column in which appears and take the determinant of the remaining elements. Here this is 4, 2 and 8, 5. So the second cofactor is that is we have deleted this row and this column, that is 4, 2, 8, 5. So I will write 4, 2, 8, 5. Similarly I will take the third element and replace it with its cofactor, that is I will delete the first row, the row in which it appears and the column in which it appears mentally. So I take the determinant of the remaining elements, that is 4, 2, 6, 3. So this will become 4, 2, 6, 3. Having done this with the first row, similarly we take the second row. Now 4 appears in the first column, that is the first column and second row. So I will delete this column and this row and take the determinant of the remaining elements, that is 2, 3, 3, 5. So I will write here 2, 3, 3, 5. Similarly here 6, I will delete the row and the column in which it appears, that is this row and this column. Now the remaining elements are 1, 3, 2, 5. So I will write here 1, 3, 2, 5. Similarly 8 is in this row and this column, that is this and this, that is 1, 2, 2, 3 will be the cofactor, that is 1, 2, 2, 3. Similarly this 2 appears in the third row and first column, and we mentally delete these 2 rows and columns in which 2 appears and take the determinant of the remaining elements. Here it is 2, 6, 3, 8. So I will write here 2, 6, 3, 8. Now similarly here 3 appears in the third row and second column. I delete third row and second column, third row and second column, and take the determinant of the remaining elements. Here it is 1, 4, 3, 8. So I will write here 1, 4, 3, 8. Similarly the last element is 5. It appears in the third row, third column. So I will delete these this row and column. Now I will get 1, 2, 4, 6. So I will write here this is 1, 2, 4, 6. Now this matrix is called the cofactor matrix of the given matrix. Now an adjoint matrix is the transpose of the cofactor matrix. Now one thing is to be remembered here, we have to change the signs alternatively. Here we have to change the signs alternative here, because according to the law of cofactors, this first element will be positive and second will be negative. This will be positive, third will be negative, this is positive, this is negative, this is positive, this is negative, and this is positive. Why? Because it is, we see here, if A12 is the element, if this is the element, this 2, it is at a position that is A12. Now the sign of this cofactor this cofactor, that is the second cofactor, is equal to, that is minus 1 raised to the power of the subscripts, that is 1 plus 2. Here we see this is minus 1 raised power 3. Now minus 1 raised to an odd power gives us minus 1. Similarly, if I have the third element, that is this, the position of this element is this 3 is at so I will write here, this 3 is at A13. Now the sign is given by minus 1 raised to the power of the subscripts here. Now the subscript is here 1 plus 3, so I will write 1 plus 3. So this is minus 1 raised power 4. Now minus raised to an even number gives us plus 1. Therefore I have written here it is positive. Similarly, this element here, this 4, it appears at A21. The address of this element is A21. That is A21. Now the sign of the cofactor, corresponding cofactor of this element is, that is equal to minus 1. This is the general formula. We add this subscripts and raise these subscripts to the power, to the exponent of minus 1. That is, here this is 2 plus 1. Now here it is minus 1 raised power 3. So the sign will be here, because minus power raised to an even number, odd number gives us minus 1. So here I have written this minus sign. Now similarly, if this is the element, the address of this element is A33. That is third row and third column. Now the sign is here positive. We will see why. That is A33. Now to get a sign, we take the minus 1 and raise it to the power of the addition of the subscripts, that is 3 plus 3. Now 3 plus 3 is 6, that is minus 1 raised power 6. Now minus 1 raised to an even is plus 1. Here we can see this is the positive here. This cofactor is positive. So the general rule is minus 1 raised to an odd power is minus 1, and minus 1 raised to an even power is 1. And we know from the earlier video that cofactor is a minor, that is cofactor is a minor with proper sign. That is the difference between minor and the cofactor is of the sign. That is, cofactor is usually with its sign. The sign of the cofactor depends upon the element, the position of the element. That is the row number and the column number, as we have seen in these examples. Now this was all about the cofactor matrix. Now the adjoint. So I will rub this out. We will see the adjoint matrix. Transpose of cofactor matrix is called the adjoint matrix. So I will write, if A is a general matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now if A is the general matrix, now the cofactor of this element is, and this matrix is, that is that is given by the C11, C12, C13, that is the adjoint matrix, C21, C22, C23, similarly C31, C32 and C33. Now this is the cofactor matrix. Now the adjoint of the cofactor matrix gives us the transpose of the cofactor matrix gives us the adjoint matrix. Now the transpose of this matrix, this cofactor matrix, that is C dash, means the transpose of this matrix, this adjoint matrix, that is equal to, we will replace the row with the column. So this row will become column. So this will become here C11, C12, C13. Similarly, this will become C21, C22 and C23. Similarly, this row will become the column, that is C31, C32 and C33. So therefore adjoint, which is denoted by this adjoint A of A, is equal to the transpose of C. So this is the adjoint matrix. This is the adjoint matrix. Adjoint matrix. Now we will give an example on the adjoint matrix. So for that I will rub this here. Let us take an example. If I have a general matrix, that is, or I have a matrix like this: 1 2 3 2 1 0 4 5 2. If this is a matrix, now the adjoint of this matrix, as we have seen, is given by, so I will write here, that is C is equal to, so I will write here, I will write the cofactor matrix here, that is the cofactor of the first element is this row, this column, 1 5 0 2. So I will write 1 5 0 2. Similarly, the 2 is here, delete this row and the column, we get 2 4 0 2, that is 2 4 0 2. Similarly, the third one is the cofactor of this element is, delete the row and the column in which appears. Now the remaining elements are 2 4 1 5. So I will write 2 4 1 5. Similarly, here this is 2, delete the row and the column in which it appears, we get 2 5 3 2, that is 2 5 3 2. Similarly, 1, delete the row and the column, we get 1 4 3 2, so that is 1 4 3 2. Similarly, delete the row and the column, now row and column, we get 1 4 2 5, we get 1 4 2 5. Similarly, this 4, we delete the row and the column, we get 2 1 3 0, so 2 1 3 0. Similarly, this 5 appears in this row and this column, we get 1 2 3 0, so here it is 1 2 3 0. Similarly, we have this 2 here, now delete the row and the column in which it appears, we get 1 2 2 1, that is 1 2 2 1. Now we have to give the proper sign. We have seen the sign changes alternatively. First is positive, second is negative, third is positive, fourth is negative, fifth is positive, sixth is negative. Similarly, this is positive, this is negative, and last one is positive, because a cofactor is a minor with proper sign, and sign is given by the address, the subscript of the address, and that is raised, that is equal to the I plus j, and that is sign is given by -1 raised to the power of the addition of the matrix in which the element appears. Here we can see this is A13. This is A13. Here this is 1. A13 is equal to, now we will add the subscripts here, that is 1 plus 3, that is -1 raised power 4, that since -1 raised to the even number is A1, that is +1. Here it is plus, here it is minus, because of the law of the cofactors. Okay, I have shown in the previous example how it is done. Now this is the cofactor matrix, and I have given the proper sign to these. Now solving further, this will become here. Now 1 into 2, 1 2s are 2, minus 5 zeros are 0, so we will get 2 minus, should I elaborate this here? I should elaborate this. Now because of the lack of the space, I will try to make it smaller here. Now this is 1 into 2, that is 2 minus 5 into 0, that is 0. Similarly here the sign is minus, so I will write here minus. Now here it is 2 2s are 4, 4 minus 4 zeros are 0. Similarly here this is 2 5s are 10, that is 10, minus 4 1s are 4. Similarly here the sign is minus because of the law of the cofactors. Here 2 2s are 4, 4 minus 5 3s are 15. Similarly here the element will be 2 1s are 2, minus 4 3s are 12. Here we have the minus. Now 1 5s are 5, minus 4 2s are 8. Similarly here this is 2 zeros are 0, this is 2 zeros are 0, minus 3 1s are 3. Here it is minus is with it, that is 1 zeros are 0, minus 2 3s are 6. Similarly here it is positive, so 1 1s are 1, minus 2 2s are 4. Now the matrix we got is, that is, this is 2. Now here it is minus 4. Here 10 minus 4 is 6. Yes, it is 6 here, obviously. Now 4 minus 15 is 4 minus 15 is minus 11. Now we have another minus, so this will become plus 11. Similarly 2 minus 12 is minus 10. Here 5 minus 8 is minus 3, and we have another minus in multiplication, so this will become plus 3. 0 minus 3 is minus 3. Now this will become plus 6, and here it is minus 3. So this matrix, so this is the cofactor matrix of the given matrix. Now implies, I will write here, this is the cofactor matrix. This is the cofactor matrix of the given matrix. Now the transpose of this matrix gives us the adjoint matrix. That is, adjoint matrix is given by the transpose of the cofactor matrix. Now the cofactor matrix is here. This is the cofactor matrix. Now transpose means interchanging rows with column. So I will write here, transpose in matrix means interchanging rows with columns. Now this is the row, and I will replace it with column. So if here it is row, I will make it column. So this is 2 minus 4 6, I will make it column, that is 2 minus 4 and 6. Similarly I have, this is row here, 11 minus 10 3, this will become column, that is 11 minus 10 and 3. Similarly here it is minus 3, 6 and minus 3, it is row, and I will make it here column. So minus 3, 6 and minus 3. So this is the cofactor, sorry, this is the adjoint of the given matrix. Now I repeat quickly. If A was given us a matrix, then first we found the cofactor matrix. After that, to find the adjoint matrix, we transpose the cofactor matrix. That is, we transpose this matrix. The resulting matrix will be the adjoint matrix. So this was all about the cofactor matrix and adjoint matrix. I hope you like the video. If you really like, please subscribe and share. And accordingly, we will go to the inverse of the matrix. That is very important topic. And from there, after that, we will see the economic applications of the linear algebra. That will be to form a system of linear equations, or we have to find the input output problems. For that we use these matrices. Thank you. So for more videos on mathematical economics series, please subscribe our YouTube channel Econ Maths. Also like, comment and share. Thank you. Eyvallah.